We will look at the scattering cross section between two particles like electrons or electron and positron or any charged particle which could be described using Dirac equation. So, let us go back to our earlier discussion on the scattering cross sections, where we had said that the transition rate per unit volume can be written in terms of the transition amplitude, like this WFi, let me denote this transition rate equal to TFI square over whatever is the time taken for this thing to per unit volume. Okay. So, TFI as we know is the transition amplitude for phi I to go to phi f when it undergoes an interaction to phi f when it undergoes an interaction in time interval t and in a volume spatial volume V. Okay. So, usually we consider that there is no interaction before this with outside this time interval. One way to see it is that if you consider the Rutherford kind of scattering, a particle which is coming from in the beam coming towards this one is free actually until it comes close to the gold foil or whatever the nucleus that it will interact with, and there is a short time interval where the interaction happens and then it flies off again asymptotically as a free particle. So, that is the kind of picture we have. Now, we had in the earlier lectures described TFI as 2 pi power 4 delta P A plus P C minus P B minus P D. So, let me first consider the TFI itself is equal to this into whatever is the normalization constant N A, N B, N C, N D and M invariant amplitude M. This is for wave functions like n e power I p x. So, there is a particle initial particle with momentum say phi a with momentum p a coming in, after interaction goes out as phi b with momentum p b, and it is interacting actually with another particle phi c p c, which goes to phi d with momentum p d. So, this case each of the normalization we consider as N A, N B, N C, N D. Invariant amplitude we had written down earlier. In the case of wave functions which obey the Klein-Gordon equation, as well as the case of wave functions which obey the Dirac equations. So, what we want in the transition rate is T f I square, the probability square, probability amplitude square gives the probability. So, this gives me 2 pi power 4, and let us write the delta function, two of them are there. So, let me write it first as d p a plus p c, the initial momenta, p b minus p d, final momenta, and duplicate it. There is another p a plus p c minus p b minus p d when you square it, and you have an n a, n b, n c, n d square invariant amplitude square. n a, n b, if okay, we will come to the normalization later. First, let us look at 2 pi power 4 delta 4 p a plus p c minus p b minus p d square. Okay, this I can split into 2 pi into delta E a plus E c minus E b minus E d into 2 pi delta 3 momentum p a plus p c minus p b minus p d, 2 pi power 3. So, when I have two such delta 4s, I have one term or one part 2 pi delta E a plus E c minus E b minus E d into the same thing 2 pi delta E a plus E c minus E b minus E d. So, let me write. So, the first one as it is E a plus E c minus E b minus E d. Second one in the integral form minus e power minus I E a plus E c minus E b minus E d t integrate over t dt, and let me take the interval as minus t by 2 to t by 2, where essentially the interaction happens. So, this now look at this, the integral inside this has an exponential E a plus E c minus E b minus E d t. Owing to the other delta function, this can be set to equal to 0. So, essentially we have 2 pi delta E a plus E c minus E b minus E d integral dt minus t by 2 plus t by 2. So, that will give me 2 pi one delta function as it is and factor t, whatever is the time interval. In a similar way, we get 2 pi power 4, not 2 pi power 4, we have taken the time part away, energy part away, only the 3 momentum now. P a plus P c minus P b minus P d square of it, let me denote it as square of it, equal to one of the delta functions as it is P a minus PA plus PC minus PB minus PD, and then the conjugate variable, which is basically the space coordinate. And now we have a 3-dimensional thing, therefore, it is the spatial volume relevant to that is coming into picture when we are integrating over the other, or when we consider the other delta function as an in the integral form and then integrate it over that. So, P f I square is 2 pi, now I can write it as 2 pi 4 P a plus P c minus P b minus P d in for momentum, and it is delta 4, and you have a T and a V, the time interval and the volume involved there, and you have an N A, N B, N C, N D square and invariant mass square, invariant amplitude square. Now, W f I, the rate is T f I over T v per unit volume, rate per unit volume is now 2 pi, the T v cancels with this T v. So, what you have is 2 pi power 4 delta P a plus P c minus P b minus P d, the 4 momenta, delta 4, T v cancels with this, and you have an N a, N b, N c, N d square invariant amplitude square. Now, when we take phi to be 1 over root v, in the case of 3-dimensional box normalization, we take this minus I p x, and that will give you, as per our earlier this thing, rho is equal to 2 E n square. If you remember, please look back. In the case of Klein-Gordon equation, we had actually obtained this rho equal to 2 E n square as our density, probability density, or if you multiply it by E, then it will be charge density. That is the number of particles essentially that it will correspond to. So, this is 2 E over V for this. So, this actually says that there are 2 E particles in V volume. So, the density is 2 E over whatever the volume V. Okay. So, that is one way to interpret this. So, with all this, that put in W f I is equal to 2 pi power 4 delta 4 P a plus P c minus P b minus P d 1 over V V square, because each of this, so this says that n is equal to 1 over root V. So, we have not 1 over, this is into, yes, 1 over V square, which is N a, N b, N c, N d, and you have the invariant amplitude square. We need want to relate this to the number of the cross section. Okay. So, the cross section of the scattering process is equal to, or cross section of the interaction is, rate per unit volume into number of final states per particle divided by so the cross section into, so let us cross section into initial flux into target density. Okay. So, the cross section times initial flux times the target density is essentially going to give you the WFI, the rate, into the number of final states whenever it is going into available final state into per particle. So, this is what basically the cross section is. We had discussed this earlier. Now, number of final states is equal to, as we said earlier, the phase space volume V plus d3V when we consider a volume element between P and P plus dP, then it is V d3P over h cube, 2 pi h cross cube, and since we are taking h cross to be equal to 1, this is 2 pi 3 for h cross is equal to 1 in our units. So, the number of final state, we said in volume V we have essentially 2E number of particles, that is what the normalization told us. So, 2E particles in V volume will give you final state available for one particle is equal to V d3P over 2 pi 3 2E. For 2E it is this much, and then for one particle it is 1 over 2 pi of this. And initial flux equal to number of particles per unit volume into the velocity of the particle, right. Essentially look at what is happening. There is a beam which is going in. So, what is the initial flux in a cross sectional area? Number density and in a unit area cross section. If you take the number density for unit area cross section, the volume per unit time is going to be this unit area into V t corresponding to that. And when t is equal to 1, it is just V. So, it is cross section times V, the area times V t is the volume. So, this times for unit area it is equal to 1 into V into 1. So, that is the volume. So, 1 into V into 1 is V essentially. Since we are considering initial beam as the A particle beam, and let me denote it by V A. So, this is the magnitude of the velocity V A. And if the other particle is a target particle which is at rest in the lab frame, target density is to be considered, that is going to be 2EC, the other particle. So, essentially what we have is, initially you have particles of type EA and A and C. So, same volume V. Now, if we consider colliding beams, then this V is actually the relative V. So, there are two particles, then one is going with the velocity V A, the other is going with the velocity V C. So, in the rest frame of C type of particle, one beam, the other we will have velocity V minus V A minus V C, right. So, in this case, this is for fixed target. So, for colliding beams, we have initial flux equal to 2 E A over V is the number of particles, but then this is going to be V, the magnitude of the relative velocity, V A minus V C. Target density then is 2 E C over V, because it is in the rest frame of that particle that we are considering the initial flux. That is why the velocity is the relative velocity. So, that will give you the cross section equal to W F I into V d3 P B over 2 pi 3 2 E B V d3 P D over 2 pi 3 2 E D. Initial flux times target density is V A minus V C 2 E A times 2 E C divided by V in each case. So, we have a V power 4 W F I over V A minus V C, magnitude of that, 2 E A 2 E C, and the number of phase space V is gone, d3 P B over 2 pi 3 2 E B d3 P D over 2 pi 3 2 E D.